Really fascinating stack of sources, all kind of circling around one big question. What are the absolute lightest particles known in the universe?
Yeah, we're diving into particle physics here, looking at what the sources tell us about particles with the tiniest masses, or, well, maybe no mass at all.
And our goal, our mission for this deep dive is really to walk you through this stuff.
Exactly. We want to help you make sense of what physics says about these super lightweight things and pull out the key takeaways.
Because understanding particle mass is just so fundamental, isn't it? It shapes everything.
Oh, absolutely. From atoms to, the whole structure of the cosmos.
And today it's all about the featherweights, the lightest of the light.
Right. So the standard model, which is our best current picture of fundamental particles,
Yeah.
it actually predicts that some particles are truly massless. No mass whatsoever.
Okay, and these are the ones that carry forces.
That's them. The gauge bosons, the force carriers.
Like the photon, that's one we sort of deal with constantly, right? Light.
Exactly. And the sources are really clear on this. The photon's mass is 0. As far as we can tell, precisely 0.
Well, it carries the electromagnetic force. So light, electricity, magnetism, even chemistry.
Yep. Chemical bonds holding atoms together. It's the quantum of the electromagnetic field.
And properties. They always travel at c, the speed of light.
In a vacuum, yes.
Always.
And their energy and momentum, it's all tied up in their frequency or wavelength. Remember, EHF.
AHF, PF.
All right.
Right. So no rest mass, just energy from moving.
Precisely. It's purely relativistic.
Yeah.
And, the really cool thing the sources point out is why it has to be massless.
Oh.
The theory behind it, quantum electrodynamics, QED, it fundamentally requires a massless photon.
It wouldn't work otherwise.
Not in the way that matches reality, no.
Yeah.
That 0 mass is why the electromagnetic source can reach out over, well, infinite distances. And experiments have tested this like crazy.
And they confirm it consistent with 0?
Down to incredible precision.
Yeah.
It's just fundamental to how we see and interact with everything.
Okay, so photon, massless, carries electromagnetism. What about the force inside the atom's nucleus? The strong force.
The strong nuclear force, that's mediated by the gluon.
And the gluon is also massless.
Theoretically, yes. The standard model, specifically the theory of the strong force called quantum chromodynamics, or QCD, says its mass is 0.
Okay. And the strong force, that's what holds quarks together to make protons and neutrons, and then holds the nucleus together.
That's the one. Gluons are the glue, literally. And there are actually 8 different kinds of them.
8 types, wow. And they carry something called color charge.
Yeah, color charge, it's just the name, obviously not visual color, is the type of charge the strong force interacts with, analogous to electric charge for electromagnetism.
Got it. And the sources mention this thing, color confinement. What's that about?
Right, color confinement. It's a really key and kind of weird feature of QCD. It basically says that particles with color charge, like quarks and gluons, can't exist out in the open by themselves.
They can't be free.
Nope. They're always confined inside composite particles that are color neutral overall. Think protons and neutrons. You can't just isolate a single gluon and put it on a scale.
Ah, okay. So even though the theory says they're massless, we can't directly measure a free gluon's mass because they're always stuck inside something else.
Pretty much. We infer their properties, including their masslessness, from how well QCD predicts the outcomes of high-energy collisions where the strong force is dominant. The math of QCD requires massless gluons, and that math works incredibly well.
But hang on, the sources said something about gluons contributing to mass. How does that work if they're massless?
Yes, this is one of the most mind-bending things. Even though the gluons themselves are massless, the energy tied up in the gluon field inside a proton or neutron, the energy of their interactions binding the quarks is enormous. And thanks to Einstein's EMCC, that energy contributes mass. In fact, most of the mass of a proton or neutron comes from the energy of these confined massless gluons and the kinetic energy of the quarks, not from the quarks' own masses, which are tiny.
Wow. So the massless carriers of the force actually generate most of the mass of the things they hold together through their energy.
Exactly. It's a really profound insight from QCD and relativity, and definitely a highlight from the sources.
That is wild. Okay, so photons and gluons, theoretically massless force carriers. But then the sources shift gears a bit.
Right. They move on to particles that, well, for a long time everyone thought were massless, but they aren't.
The neutrinos.
The elusive neutrinos, yes.
And the sources hammer this home. They do have mass. It's incredibly, incredibly tiny, but it's definitely not 0.
They're the lightest particles we know of that actually possess mass.
And they're everywhere, right? Produced in the sun, nuclear reactors.
Supernovae, radioactive decay.
Yeah.
Yeah. But they barely interact with anything. They mainly feel the weak nuclear force and gravity. Billions are going through you right now.
Well, you don't feel a thing.
Not a thing. Makes them unbelievably hard to detect.
And there are 3 types. Flavors.
3 flavors, yeah.
Yeah.
Electron neutrino, muon neutrino, and tau neutrino.
So how did we figure out they do have mass if they're so hard to catch?
The breakthrough was something called neutrino oscillation.
Oscillation, like they change.
Exactly. A neutrino created as one flavor, say an electron neutrino, can actually morph into a muon or tau neutrino as it travels through space.
Bro.
And the physics behind oscillation, the quantum mechanics of it, only works if the neutrinos have mass. And not just mass, but different masses from each other. At least 2 of the flavors must have different non-zero masses for this flavor changing to happen.
So discovering oscillation was basically discovering they have mass.
It was the smoking gun. Definitive proof.
But the oscillation experiments, they tell us the mass differences, not the actual masses themselves.
That's right. They measure things related to the difference between the squares of the masses, like m0. But they don't tell us how heavy μ or m actually is. We don't know the absolute scale.
Okay, so how do we try and weigh them? The sources mention direct measurements.
Yeah, there are experiments trying to directly weigh them. The current frontrunner is Katrin in Germany. It looks very precisely at the energy of electrons emitted during a specific type of a radioactive decay, tritium decay.
And how does that tell you the neutrino mass?
Because a neutrino is also emitted in that decay, and it carries away some energy. If the neutrino has mass, there's a tiny effect on the maximum possible energy the electron can have. Katrin looks for that subtle effect right at the endpoint of the electron energy spectrum.
Clever. And what have they found?
They've set the best direct upper limit on the electron neutrino's mass so far. They found it has to be less than 0.45 electron volts divided by c squared.
Okay, 0.45 eV Felicia. Let's pause there. Particle physicists use these energy units for mass.ev, MeV. Can you unpack that a bit?
Sure. It comes straight from Yves C. Plater. Mass and energy are equivalent. So instead of kilograms, it's often more convenient to talk about a particle's rest energy, which is directly proportional to its mass. An electron volt, eV, is a tiny unit of energy. MeV is mega, or a million eV. G is giga, a billion.
Right.
So saying the mass is 0.45 eV seesaw just means its rest energy is 0.45 eV. And putting that into kilograms, it's unbelievably small, like 8 times 10 to the minus 37 kilograms. Tiny doesn't even begin to cover it.
8 with, what, 36 zeros after the decimal point? Okay, mind-bogglingly light.
Truly.
And the sources also mentioned cosmology. Looking at the whole universe to weigh neutrinos, how does that even work?
Yeah, that sounds crazy, right? But neutrinos are so numerous, leftovers of the Big Bang plus all the stars. There are hundreds of them in every cubic centimeter of space, whizzing around.
Okay, so sheer numbers matter.
Exactly. Even if each one has a minuscule mass, altogether they add up to a significant chunk of the universe's total mass energy budget. And that collective mass has a gravitational effect.
Gravity.
It slightly changes how gravity pulled matter together over cosmic time, influencing how galaxies and clusters of galaxies formed. By looking at maps of the cosmic microwave background radiation, the afterglow of the Big Bang, and the large-scale distribution of galaxies today,
Yeah.
cosmologists can figure out how much extra gravity from neutrinos would be consistent with what we see. This gives them a limit on the sum of the masses of all 3 neutrino types,
And those limits are?
often even tighter than the direct limits. Current cosmological data suggests the sum of the 3 masses is probably less than about 0.12 eVc.
Wow, so less than Katrin's limit for just the one type. That's fascinating. So why is this tiny neutrino mass such a big deal? Why should you, listening at home, care?
Well, it's huge because the original standard model, the really successful theory we talked about, it predicted neutrinos were massless, like the photon. So finding out they do have mass, that was a massive discovery. It told us unequivocally that the standard model isn't the complete story. There has to be new physics out there to explain where this mass comes from.
It broke them all.
In a really important way, yes. It points towards deeper theories. Plus, as we just said, even that tiny mass affects the evolution of the entire universe. Small particle, big consequences.
Okay, before we summarize the lightweights, the sources also brought up the electron kind of as a benchmark.
Yeah, good point. The electron is the lightest stable particle that also carries an electric charge.
It's fundamental, right? Orbits the nucleus, carries current. Absolutely.
It's a fundamental lepton stable negative charge. Can't imagine chemistry without it.
And its mass. The sources said about 0.511 MeV.
Right. Now notice that's MeV mega electron volts. 500,000 EVCR.
Okay.
Compare that to the neutrino limit we just talked about, less than 0.45 EVCR. The electron is more than 1,000,000 times heavier than that upper limit for the electron neutrino.
Whoa, okay. So electron light compared to a proton, but an absolute heavyweight compared to a neutrino.
Exactly. Puts things in perspective. Still fundamental, still incredibly important for atoms and chemistry, but definitely in a different mass category than the neutrinos.
All right, this has been great. Let's try and sum up this parade of lightness based on the sources, maybe going from heaviest we discussed down to massless.
Sounds good. So, for perspective, the lightest stable charged particle, the electron. Mass around 0.511 mc/Kihua.
Okay, then plunging way down in mass, we hit the neutrinos.
Right. The lightest particles known to have mass. We don't know the exact values, but the sum is likely less than 0.14 eVc from cosmology, and the electron-neutrino part is less than 0.45 eVc quad directly. And their mass means new physics.
Below them, we get to the theoretically massless crew. First, the gluon.
Yep, carrier of the strong force. QCD says mass equals 0, 0, but confined so we don't see them freely. And remember, their energy gives protons most of their mass.
And finally, the champion of
The
masslessness.
photon, carrier of the electromagnetic force. Mass theoretically 0, and experiments back that up completely. Masslessness gives electromagnetism its infinite range.
Just studying these particles, from the photon all the way to the neutrinos, it really pushes the boundaries, doesn't it?
Absolutely. They hold clues about the nature of mass itself, about the forces, and potentially about physics we haven't even discovered yet.
So we've taken this deep dive through the incredibly light side of the particle zoo, massless force carriers like the photon and gluon, the featherweight neutrinos that surprised everyone by having mass, and we put the familiar electron in context too.
Which leads us to a final thought, something for you to chew on.
Okay.
We know the fact that neutrinos have any mass, even this tiny amount, proves the standard model is incomplete.
Yeah.
So the provocative question is, as we get better and better at measuring these tiny neutrino masses, potentially pinning down their exact values and ordering, how might that precision measurement finally show us the path to the next deeper layer of fundamental physics? What new rules of the universe might be hiding in those tiny numbers?